Hi all, thank you for joining us for OTTER today. Our speaker will be Ian Thompson from the University of Manitoba, and he'll be talking to us about non-commutative boundaries and peaking phenomena for operator algebras. Take it away, Ian.
Okay, thank you, Meredith. So thank you for showing up and giving me a chance to speak. So I'm going to be talking about non-commutative boundaries and peaking phenomena for operator algebras. And I just want to first mention that this is joint work with my supervisor, who is Raphaël Clouâtre. And I want to just start by saying, this is going to be more on the algebraic side of things, but it's more, there's a lot of function theoretic types of stories, which may be of interest, especially to an operator theory crowd. And also a lot of the kind of theory that kind of underlies a lot of this is rooted in kind of a non-commutative convexity theory for operators, which very closely linked to something like matrix convexity. Okay, so, these kinds of weaker objects won't necessarily be C-star algebras or von Neumann algebras. And accordingly, they might be of more interest to those interested in operator theory as well. So I want to say that this should not be surprising, because there are countless function theoretic types of objects that you can naturally encounter out in the wild, and they won't necessarily be encoded in this language of C-star algebras or von Neumann algebras. So you don't have to look very far to think about this by any means. So if you think about uniform algebras or spaces of continuous affine functions, you start to realize quite quickly that these function theoretic ideas won't necessarily work out for you when you look at C-star algebras or von Neumann algebras. Okay, so in order to do something like convex analysis, just using it to characterize it in a non-commutative way through C-star algebras won't necessarily be a complete vision, or at least in some sense. But as a brief kind of outline for what I'm going to be speaking about today, I'm going to be talking about the minimal boundary of a uniform algebra, which is a classical topic in complex function theory. And it has three different characterizations in what I'm going to be speaking about today. It can be interpreted in terms of representing measures, in terms of peak points, or in terms of peak projections. So you can characterize it through characteristic functions. And so we'll be exploring these three different interpretations of the minimal boundary. And then we'll work towards interpreting these three interpretations for subalgebras of bounded linear operators. Okay, so essentially just moving the story to the non-commutative side of things and see what happens. And in the commutative setting, these all kind of encode the same notion of a minimal boundary for a uniform algebra. And so then we'll try to interpret minimality in this non-commutative setting and whether it can be talked about in kind of a sufficiently nice manner. So to start out, I'm just going to be talking very specifically about the classical setting. So if you take a compact metric space and a unital norm-closed subalgebra that separates points in X, this will be called a uniform algebra. And more generally, for a lot of what I'm doing today, you don't need metrizability. You can work with arbitrary compact Hausdorff spaces. But just, for simplicity and to make sure everything's kind of a bit nicer, we can assume metrizability, and there are some small facts here or there which may require metrizability, or it'll be quite a bit more complicated in order to establish it in the non-separable setting. So these are the basic kind of objects that I'll be working with for today. And the principal object that I care about is that of a boundary. So a boundary for a subalgebra is a subset of points in X, which is essentially a norm attainment set for the subalgebra. So what it says is that for any function in the subalgebra, you can find some point in the potentially smaller subset delta for which that point attains the norm of the function. And for what I'm going to be doing today, I won't necessarily be assuming that the subset delta is closed, but when it happens to be the case that the subset is closed, then this equivalently just tells you that the restriction map is isometric on the subalgebra. So you can really think of a boundary as kind of encoding a notion in which it trims the fat in the representation of your uniform algebra. Okay, so if you're interested in studying this uniform algebra represented on C of X, potentially it's not such a flattering kind of representation. And so maybe it's more advantageous to try and describe the smaller boundaries and find better representations of the same algebra on a potentially smaller space of continuous functions. Okay, you can also take the opposite type of philosophy if you like, and try and create bigger spaces of continuous functions, which encode a copy of the uniform algebra as well. But for what I'm doing today, the optimal choice is in some sense choosing smaller and smaller subsets to try and optimally describe your uniform algebra here. And so certainly you could consider your entire space X, and that'll be a boundary for your subalgebra, but that's not a very interesting example at all. And so you want to make potentially nicer examples. Okay. And certainly, it seems kind of non-trivial type of task to be able to create boundaries out of nothing. Okay, so if you have an abstract uniform algebra here that you know nothing about, how are you going to guarantee a boundary which isn't the entire space X? It's not entirely obvious how you could describe that, if it's even possible. So we'll do a small example here just to start out. So what if you choose a particular algebra? So particular, choose A to be the entire space of continuous functions, in which case the only boundary that you can find is the entire space X. So the reason for this is essentially by Urgén's lemma, or by metrizability. You can kind of think of this as just being a consequence of the geometry you get from the metric, is that you can create these functions which are continuous and essentially attain their norm at a unique point. And moreover, you can do that for any point in the space. And so consequently, in order for the norm of these functions to be attained over a boundary, it has to be the case that the boundary is in fact the entire space X. Okay, well, that's, unfortunately somewhat of a boring example. But, you want a more interesting example of a boundary. And this was known to Choquet back in the 50s. And here's one way you can describe a non-trivial boundary. So he was able to describe it through representing measures. And a representing measure, for my purposes, is a Borel probability measure with the property that integration against this measure agrees with integration against Dirac measure for the subalgebra. So, this kind of encodes a measure theoretic kind of problem here. And the Choquet boundary is the collection of all points in the space X for which Dirac measure is the unique representing measure at that point. So what that says is, it's the collection of all points for which you don't have any non-trivial Borel probability measures floating around in the background, which at the level of the algebra look like Dirac measure with respect to integration. Okay, so the Choquet boundary is the collection of all points for which the behavior is at least a bit more trivial in this kind of sense. And Choquet proved a very landmark kind of theorem, which is kind of great result in the theory of compact convex sets, which consequently shows this following fact. And it's that the Choquet boundary is in fact a boundary for a uniform algebra. Okay, so that's one example of a non-trivial boundary that you can find out in the wild. It's these collection of points for which Dirac measure is the unique representing measure. And, this is nice, but really the optimal choice is if you were to try and find a minimal boundary. So you want to find the smallest boundary for a given subalgebra. And in fact, it will end up being the case that this is the minimal boundary. But let me just try and motivate this problem for you and why the Choquet boundary will be the minimal boundary. So one way you can kind of try and figure this out is let's try and identify some points which necessarily have to lie in this smallest boundary for the subalgebra. And some points which necessarily have to lie in this smallest boundary can be described through the peak points. So peak point for a subalgebra is a point in the space X for which there's a function in the subalgebra that attains its norm uniquely at that point. Okay, so for you to have a norm-attaining subset, it has to be the case that you contain these points C. So necessarily, the minimal boundary must contain all the peak points for a uniform algebra. But in fact, Bishop was able to show something much stronger. Bishop showed that, in fact, the peak points are precisely the points in the Choquet boundary of the uniform algebra. Okay, so this perfectly kind of tells you what the minimal boundary must be. Okay, the peak points are a subset of the minimal boundary, but in fact, they also form a boundary because they are the Choquet boundary. So what that tells you is that the Choquet boundary is necessarily going to be the minimal boundary for the uniform algebra. So far we have two interpretations of this one kind of idea. We can describe the Choquet boundary either as the collection of all peak points, the points for which there's a function in the subalgebra that attains its norm uniquely at that point, or the collection of points for which there is a unique representing measure at that point. So you can have either this measure theoretic problem, which is a bit more abstract, or this more kind of analytic or geometric kind of condition revolving around peak points. And in concrete examples, it seems a bit easier to identify the peak points, even though these things are the same. So just as a short example to kind of demonstrate this, you could consider the disk algebra, which is the algebra of functions that are holomorphic on the open unit disk and continuous up to the boundary. Then each point on the unit circle has a corresponding function that lies in the disk algebra and actually peaks at that point that you're given on the unit circle. Okay, so it's not too hard to check that at all. And by maximum modulus principle, the only peak points that you can possibly even have are those on the unit circle. So what that tells you is that the Choquet boundary must be precisely the unit circle. Okay, so if you were to try and do this problem using unique representing measures, it might be a bit more cumbersome or kind of abstracted. And so peak points are generally nice to have in practice. Okay, so we have our two characterizations of the Choquet boundary. And now I want to describe one last way of describing it. So this is using kind of theory of projections. And you could think of peak points through characteristic functions, just replacing evaluation essentially with the characteristic functions. So the Choquet boundary is the collection of points for which there's a contraction in the subalgebra, where multiplication against characteristic function for xc just returns itself. And for any closed subset that does not contain xc, A has non-dominant behavior, which essentially exactly encapsulates kind of the notion of being a peak point. Okay, so, and I'll also just mention, of course, A is a contraction, it attains its norm at xc, and so that tells you that really this inequality in the second part of the equation here, in fact, says that you have non-dominant behavior around there. And related to this is a characterization of the Choquet boundary due to Bishop. So, or sorry, not by Bishop, it was by Glicksberg. But Glicksberg was able to show that the Choquet boundary consists of precisely those points for which the characteristic function at xc lies in the weak star closure of A once you represent it in the double dual of C of x. And so, we have these three different interpretations. And this last one I want to also just mention briefly. This characterization also naturally generalizes to a theory of peak sets. So it's not hard to kind of imagine that, you replace your characteristic function over one point with a characteristic function over a potentially closed subset. And, in fact, a similar statement is kind of true that a closed set F is a peak set precisely when the characteristic function lies in the weak star closure. And so Glicksberg showed this, noticeable improvement relating to geometry in this weak star problem. Okay, so we have these three identifications as peak points, peak projections in the sense of Glicksberg, and unique representing measures. Okay, so we have these three different interpretations that we want to try and think about in the non-commutative setting. And this is a much wider class of algebras that we're going to be studying here today. And in fact, this has been quite a large goal for many authors over the last 50 years. And so it's quite a big story that's been told over the years. And so I want to just start out by introducing the main objects that I want to care about in this kind of setting. So an operator algebra is a norm-closed unital subalgebra of bounded linear operators. And the big caveat here is that these algebras I'll be dealing with are not necessarily self-adjoint. So that kind of creates a big hiccup when you try to deal with these things abstractly, because in theory these things lack positivity in quite a large way. It could be the case that the only self-adjoint elements you have are in fact scalar multiples of the identity. Okay, so it can be quite a ill-behaved kind of structure, and these things can range wildly. And then a kind of modern trend that I want to just mention here in the kind of operator algebraic realm is in the classification program for C-star algebras. One of the kind of underlying things that people kind of care about is that you want to be able to link C-star algebras with von Neumann algebras. And in some sense, von Neumann algebras have a more rigid structural theory available to them. And so consequently, that'll kind of tell you that, those could possibly be beneficial in order to characterize C-star algebras. Or even, more generally, studying the double dual or the double commutant of a C-star algebra can be very rewarding in practice. And likewise, in order to study these non-self-adjoint operator algebras, a beneficial thing that you could possibly do is leverage the more rigid structural theory from C-star algebras. Okay, so the C-star algebra that is generated by an operator algebra is the C-star algebra that we will generally care about. And I'll actually write this out concretely why we would care about this one in particular. And it'll be denoted just by C-star of A. And then finally, just so everyone is familiar with the notion, we'll be dealing with completely positive maps. These are linear maps defined on the C-star algebra with the property that whenever you tensor with the identity representation on n by n matrices for any n, this always gives you a positive linear map. Okay, and so if you don't like tensor products, you can just view this as kind of a problem involving matrices with operators, with operator entries, and just applying the map entry-wise. Okay, and you hope that this map is positive. Okay, and just as general motivation why completely positive maps weren't appearing in the beginning is that for commutative C-star algebras, the positive linear maps are precisely the completely positive maps. And in fact, in some sense, the completely positive linear maps are, in some sense, a natural generalization of positive linear functionals. So one reason for this is that you have a type of Hahn-Banach type extension theorem for these types of linear maps. And so they can naturally encode this kind of structural theory. And also that, spaces of C-star algebras, they need to use completely positive linear maps quite frequently. So if you think about the characterizations of nuclearity or even conditional expectations, the notions of completely positive linear maps appear all over the place in these kinds of theories. Okay, so these kinds of maps are quite important, and they appear in the background in the commutative setting. For instance, when you try to integrate it against a probability measure, this will be a completely positive linear map. And moreover, it's a positive linear functional. Okay, so the natural generalization should be a completely positive linear map. And so I want to be very careful to draw out the analogy of how we establish the non-commutative type of theory here. So in the classical setting, we dealt with norm-closed unital algebras. In the non-commutative setting, the exact same thing will be true, except we'll be working with spaces of bounded linear operators. And well, we were dealing with spaces of continuous functions before, and this isn't the same thing as the bounded linear operators. So we need some C-star algebra that contains the subalgebra, and it needs to be the correct choice of C-star algebra. So the correct choice is encoded in the fact that we made the assumption that the subalgebra separated points in X. So Stone-Weierstrass theorem directly tells you that A generates all of C of X as a C-star algebra. And so corresponding to this, the C-star algebra that you should care about is the one that A generates. Okay, now we want to try and interpret these notions of peak points, okay, the points for which there is a unique, or for which there is a function which has its norm attained uniquely at that point, unique representing measures, as well as the peak projections. And throughout this whole discussion, certainly evaluation is making quite an appearance. You need to be able to kind of characterize evaluation in a non-commutative setting in order to perfectly encapsulate this function theoretic story. And so accordingly, you could think of irreducible representations as being your evaluation maps, but a just as fruitful kind of interpretation of this is thinking of your evaluation maps as being your pure states for the C-star algebra. So these are both perfectly fine kind of interpretations, and I'll be exploring both of these in a bit. And then finally, also the notion of a characteristic function needs to be kind of reinterpreted in this non-commutative realm. And so the exact kind of characterization of this property is in the sense that, well, these characteristic functions are self-adjoint idempotents, and they lie in the double dual of the C-star algebra. Okay. And then finally, in order to interpret representing measures in this non-commutative realm, we need a corresponding notion. So a representing measure at a point was a Borel probability measure, okay, where integration against that Borel probability measure agrees with integration against Dirac measure for the subalgebra. And integration against a probability measure, as we just mentioned, would be a completely positive linear map in this setting. So we have some completely positive linear map, and in fact, over the subalgebra, it agrees with evaluation, because that's integration against Dirac measure. So thinking about evaluation as an irreducible representation, the sensible kind of generalization is that these should be completely positive linear maps with the property that they agree with an irreducible representation over the subalgebra. And again, there are more general kinds of theory of representing measures that people may study. But for my purposes, this is the kind of case that I want to talk about today. Okay, so my main kind of questions about these kinds of objects in forming this non-commutative story is how you interpret these three ideas of unique representing measures, peak points, and peak projections. And in the commutative setting, we saw that these three things were all the same. And so, the same kind of question holds. Are these things the same in a non-commutative setting? And moreover, the point was that these three things all encoded the minimal boundary, which was in fact some kind of optimal representation of your uniform algebra. And so corresponding to this, the final question is whether there is a minimal boundary, how to interpret this, and does it even exist? So, these kinds of problems have been thought about for a good half of a century. And so, there has been lots of non-trivial work developed on these kinds of problems. And the first one I want to introduce is the idea of a non-commutative unique representing measure. This is known as a boundary representation. And a boundary representation for an operator algebra is an irreducible representation with the property that it has a unique completely positive extension of its restriction from A. And essentially, this encodes exactly what the slide on the analogy was saying, is that if you think about a representing measure as a completely positive map, which agrees with an irreducible representation over A, then a unique representing measure in the non-commutative sense should be an irreducible representation with this unique extension property for the completely positive maps. Okay, so this kind of perfectly encapsulates the notion of a unique representing measure for a non-commutative setting. And, as we had mentioned earlier, the collection of all these things was called the Choquet Boundary. And so accordingly, the non-commutative Choquet Boundary is the collection of all boundary representations for the operator algebra. And so right away, you should, be thinking that this is kind of a non-trivial thing to be working with. So there's no reason to guarantee that these kinds of representations will exist at all. So if you kind of think about the myriad of possible problems that could arise by taking an arbitrary subalgebra of bounded linear operators and then saying, your algebra is generated by these boundary representations in some satisfactory way, like in the commutative setting. I mean, this is a hopelessly kind of large problem in some sense, because you hope that you have all these irreducible representations with unique extension property. I mean, it's a very kind of big problem in general. But Arvidsson had, in fact, conjectured that back in the 60s, not only are there boundary representations necessarily, but there are in fact lots and lots and lots of these boundary representations, enough to generate the subalgebra. So what that tells you is that in some sense, his conjecture was that a non-commutative Choquet boundary existed and that it was necessarily a boundary. But being able to even show that there exist representations of the C-star algebra which are not necessarily irreducible but do have this unique extension property is, in fact, even just as hard of a problem. And also to conjecture this in the non-separable setting is quite a large question. But over the good half of 50-ish years, a lot of authors were able to show it together. So Arvidsson, Mullay, Solel, Dirichlet, McCullough, Kleski, Davidson, and Kennedy all made advancements towards this kind of problem. And together, this is formulated as saying that the collection of all boundary representations, or the non-commutative Choquet boundary, is a norm attainment set for the subalgebra. So the analogy should definitely be that the non-commutative Choquet boundary is in fact a boundary. Okay, so there always exist boundary representations. There's always lots of them, enough to generate the algebra A. So in some sense, the non-commutative Choquet boundary is a boundary. But I'll ask you to keep a pin in that and just remember this because it'll come up again later. Okay, and when I introduce the notion of what I think a boundary should be, it won't necessarily exactly be encoded in this result, but it's very much related to it. Okay. And so if you've been kind of clocked out at this point and you're not really kind of motivated by this kind of problem, I also just want to say that the kind of proof that underlies this is a super, super powerful application of dilation theory. And it also subsequently has motivated a new formulation for non-commutative convexity, which is in some sense a natural completion of matrix convexity. Okay, so if you're interested in those notions of NC sets and things like that, maybe you would find these kinds of works to be interesting. Okay, so we have our notion of a non-commutative unique representing measure, and it's encoded in the boundary representations, these irreducible representations with the unique extension property. And I now want to try and interpret these next two interpretations of the Choquet boundary in the non-commutative setting. So we had our interpretations as peak points and peak projections. And there have been lots and lots of interpretations of peak points over the years. So Arvidsson himself studied these, but also Davidson, Clouâtre, Blecher, Hay, Hartz, and really many other authors as well that I can't all list. But Raphaël and I had proposed a handful of new candidates for peaking that you can also consider. So you could think of evaluation maps as encoding either irreducible representations or pure states. And so accordingly, we have a kind of corresponding non-commutative notion which reflects each of those kinds of interpretations. So for the representation side of things, an irreducible representation of the C-star algebra is said to be a local A-peak representation if you can find some operator in the subalgebra that attains its norm in finite dimensions under pi better than it attains its norm in finite dimensions over any other irreducible representation that is not unitarily equivalent to it. Okay, and so if you were to try and trace back these details in the commutative setting, where C star of A is replaced by continuous functions over some compact Hausdorff space, then you can see that these finite dimensional subspaces will disappear because your irreducible representations will be one-dimensional. In which case, we're just left with the statement that pi of A is bigger than sigma of A for any irreducible representation sigma that's not unitarily equivalent to pi. And essentially by identifying the irreducible representations with evaluation, this exactly encodes the statement that pi is in some sense the evaluation map of a peak point. Okay, so you could think of it in this kind of sense. And I really think that the finite dimensional subspaces that are appearing here are somewhat necessary, but I'm not even sure if they do a good enough job as far as characterizing peaking completely. Okay, or at least if you have an interest in producing a non-commutative Bishop theorem. But one different kind of variation on this essential definition is that you can have a characterization of this in the state space. So a pure state for a C-star algebra is an A-peak state if there is an operator in the subalgebra with the property that phi of A star A is bigger than psi of A star A for every state, which is distinct from phi. And moreover, it only suffices to check over the states, the pure states here, okay? So any state which satisfies this property will necessarily be pure. And moreover, you only have to check for states that are pure states that are distinct from it. So we have two notions of peak points encapsulated in irreducible representations in pure states. And these will be the notions that we're going to be considering. And then finally, I'm going to talk about this last kind of characterization of peak projections, and then we'll conclude by comparing these three different notions. So in Glicksberg's characterization, he identified the Choquet boundary as the points for which the characteristic function against it is in the weak star closure of A. And you can also identify peak points through characteristic functions. But those characteristic functions that we used, in fact, were characteristic functions over closed subsets. So we need some notion of non-commutative topology to be able to formulate this and talk about it in a non-commutative sense. So this was introduced by Akemann back in the 60s when he was studying one-sided ideals of C-star algebras and the Stone-Weierstrass problem. And Akemann said that a projection in the double dual of a C-star algebra is closed if you can find a decreasing net of contractions converging to it in the weak star topology, and that Q is open precisely when the identity minus Q is closed. So these kinds of projections are always kind of abundant in some sense, because you can kind of generate a lot of these types of projections through the L infinity functional calculus. And if you look at these, in particular in the commutative case, and you look at a characteristic function over some measurable subset, then that characteristic function is closed as a projection precisely when it's a characteristic function over a closed subset. Okay, and likewise, it's a characteristic function which is open in the sense of Akemann precisely when the subset you're working with is open. Okay, and this can be a super powerful tool in the non-commutative realm. One main reason for this is that you have a non-commutative Urjan lemma at your disposal. Okay, and since you have this non-commutative Urjan lemma, you can really do quite a lot with respect to kinds of peaking types of behavior for C-star algebras. But also on the flip side, I also just want to mention for a word of caution is that Akemann's non-commutative topology is not a true blue kind of topological thing in some sense, because even if you were to take the supremum of two projections, this may not necessarily be closed if the two projections you're working with are closed. Okay, so supremum of closed projections isn't always closed, and that can be kind of troublesome. And there are some other troublesome facts that you can run across in this kind of realm. But it does the job particularly well with respect to these peaking kinds of ideas. And if you're not motivated enough that these kinds of closed projections are always abundant and you're actually secretly running into them all the time, here's one example which will be particularly relevant for us. So if you have a state on a C-star algebra, then you can form its left support projection, which is the unique projection in the double dual, which is the orthogonal complement to the projection determined by the left ideal of the weak star extension of the state omega. And whenever your state is in fact pure, then this left support projection is closed. Moreover, if you were to do a similar thing involving support projection of star representations, you'll get a central projection in the double dual of the C-star algebra. And in fact, this will always be closed as well. Okay, so you have a very nice example of a closed projection, which will always be available to you and kind of important for our purposes. Okay, so now we want to translate this information about C-star algebras to a problem encoding operator algebras, because really you need to encode the kind of operator algebraic peaking kind of phenomena here, rather than just doing it at the level of the C-star algebra. And this was introduced by Hay back about a decade or something ago. And he introduced the notion of a peak projection as being a closed projection for which you can find a contraction in the subalgebra with the property that AQ multiplied by Q, or sorry, AQ equals Q. And then for any closed projection that's orthogonal to Q, A essentially has non-dominant behavior over the image of this projection. And so if you'll recall, towards the beginning, this kind of exactly describes the notion of a peak point in the commutative situation when you identify this contraction with being a function in the uniform algebra and identifying these projections with being characteristic functions over closed subsets. Not only that, but you can see now that how this kind of relates to a theory of peak sets rather than just peak points in general. Okay. And so the natural kind of question associated to this kind of property, like we saw in the commutative setting, is whether you have a non-commutative Glicksberg theorem available to you. And in fact, the surprising thing is that you do have a non-commutative Glicksberg theorem available to you due to Blecher, Hay, Neal, and Reed. They were able to show that for a separable operator algebra, the closed projections that are A-peak projections are precisely those that lie in the weak star closure of A in the double dual of the C-star algebra. So I also just want to highlight the work that these authors have done, because they've done a really great job at kind of characterizing the finer properties about these non-self-adjoint operator algebras, which are in some sense a lot worse to work with because you don't have positivity kind of available to you in general. So building up very minute facts and very technical facts, which are quite amazing. So facts about contractive approximate identities and one-sided ideals, and also this peak interpolation stuff, as well as a theory of hereditary subalgebras for non-self-adjoint algebras and all that. So really, they've done quite an amazing job at building up these finer properties related to structural theory of non-self-adjoint algebras, despite having the lack of an adjoint available to you. Okay, and when you think of the kind of typical example of what a contractive approximate identity is for a C-star algebra, it consists entirely of positive operators. So there's no hope in trying to adapt that kind of idea to a non-commutative setting in theory, or sorry, a non-self-adjoint setting in general. Okay, so we have our three characterizations. We have our A-peak projections, which are essentially our peak points thought of in the lens of projections. We have our NC peak points being characterized as either irreducible representations with a particularly nice spatial norm attainment feature, or our peak states, which essentially a kind of corresponding notion of peaking in the sense of pure states. And then we also have our non-commutative unique representing measures, which are our boundary representations. Okay, these are the irreducible representations of the C-star algebra, which have a unique extension property with respect to the space of completely positive linear maps. And so now I want to compare all these definitions for you and try and summarize how these different properties can relate to one another. So if you have a separable operator algebra and a state for your C-star algebra, then the left support projection being in the weak star closure of A is precisely equivalent to it being an A-peak projection by that non-commutative Glicksberg result by Blecher, Hay, Neal, and Reed. But then we also have to relate these other conditions. The state being an A-peak state, GNS representation being a local A-peak representation, and the GNS representation being a boundary representation. Okay, so the third and fourth conditions kind of resemble our peaking kind of behavior for states and representations. The second condition represents our peaking behavior for projections. And then the last one, 0.5 here, represents our non-commutative unique representing measures. And in fact, while 1 and 2 are equivalent, these all get weaker, and this result is in fact strict. Okay, so these can never be actually entirely the same. And so you don't have these interpretations of the non-commutative Choquet boundary as kind of being either peak projections, peak points, or non-commutative unique representing measures in this kind of sense. But there's at least a relationship between these properties that you can establish. And for the final portion of this talk, what I want to talk about is minimality of the non-commutative Choquet boundary. Okay, so in the classical setting, the Choquet boundary, which is the collection of all boundary representations or unique representing measures, was a boundary due to the landmark theorem of Choquet. And in fact, it was a minimal boundary by that theorem of Bishop, which described the peak points as precisely those which are boundary representations. So my remaining question is, how can you interpret minimality? And especially due to the work of all those authors, Arvson, Kennedy, Davidson, Dirichlet, McCullough, Mallet, Solow, and Kleski, they were able to show in some sense that the non-commutative Choquet boundary is a boundary, but is it a minimal boundary in the correct kind of sense? And so this is what I want to talk about to close out the talk. But in order to do so, one of these irreversible directions is very important. Okay, so the direction 5 implies 4 doesn't hold in general, but this kind of encodes some notion of this problem of minimality. Okay, so to see where this counterexample lies, consider a compact convex subset of a locally convex topological vector space. Then you can form a subalgebra consisting of 2x2 matrices of continuous functions over K, where they're upper triangular with constant diagonal. And the upper right-hand corner, you take functions which are in the closed linear span of the identity together with the continuous dual of E together with those functionals that are adjoint as continuous functions. And if you have an extreme point in this set, which is not exposed, then evaluation at this extreme point, tensored with the identity representation of 2x2 matrices, will give you a boundary representation that is not actually a local A peak representation. Okay, so there are examples out here which demonstrate a failure of this property, and they're at least the example we were able to find is very closely linked to a convexity type of theory. And so it's kind of interesting for the reason that really these notions of boundary representations encode notions of non-commutative extreme points in reality. And yeah, it's kind of interesting in that kind of sense. But I'm claiming that this has an important kind of application regarding minimality of the non-commutative Choquet boundary. For this, recall that a boundary was really a subset that normed the algebra in a sufficient kind of way. And accordingly, the same thing should be true in the non-commutative setting. This should be a collection of irreducible representations with the property that these collection of irreducible representations norm the algebra sufficiently well. Okay, so a boundary should be essentially a collection of irreducible representations, which is a norm attainment set for the subalgebra, but also the norm is attained in finite dimensions. But also on top of that, you need to have that this also happens on all matrix levels. Okay, in the sense that if you have a matrix with values in the operator algebra, then you should also have this property once you ampliate in the correct kind of manner. And Raphaël and I were able to show in past work that the non-commutative Choquet boundary is in fact a boundary. And this improves on the work of all those authors, Arvson, Kennedy, Davidson, Dirichlet, McCullough, Mallet, Solow, and Kleski. It improves on their work in a very, very small amount, just an epsilon kind of amount. But I think it's kind of important, especially when you want to talk about peaking theory. Okay. And to just give you one other example, which is kind of motivation, something that I thought was kind of interesting when we uncovered it, was that up to unitary equivalence, the only boundary that you can have for a C-star algebra is the collection of all irreducible representations. Okay, so maybe this is recorded somewhere out in the theory, but as far as we could tell, we couldn't find a direct source for it. But it's kind of interesting because in some sense, this reflects the commutative situation with Urgen's lemma, you were able to find that the only boundary for the space of all continuous functions is the entire space X. And essentially the same thing is true in the non-commutative setting. And also this kind of forces a certain kind of peaking behavior to be present for C-star algebras in general. Okay, which kind of models Urjan's lemma in some sense. Okay, so I'm going to claim that if this is our notion of a boundary and we're looking for a minimal boundary, then peaking kind of behavior is important to us. And we say that A has the Bishop property if all boundary representations are local A peak representations. So this precisely says that essentially 5 implies 4 in that list of equivalences between the different characterizations actually holds. And Bishop's theorem precisely says that uniform algebras have this property. So it's true in the commutative setting. But in fact, this will fail in general if we consider that example we were looking at a second ago. So you form this algebra consisting of upper triangular matrices. You can find a boundary representation, which is not a local A peak representation. And so A does not have the Bishop property here. Okay, so that gives you a nice example of where the Bishop property fails here. And so you can't really get a non-commutative Bishop theorem. But the thing is that this property exactly encodes the non-commutative Choquet boundary actually being a minimal boundary. Okay, in the sense of the previous slide, where a boundary is interpreted as a collection of irreducible representations that are essentially a norm attainment subset for the subalgebra in finite dimensions, but also in all matrix levels in finite dimensions. Okay, and this wouldn't be so great if there weren't actually nice examples which demonstrate that actually the non-commutative Choquet boundary can be viewed as a minimal boundary in the non-commutative setting. So first of all, C-star algebras have this property. So they have in some sense, a non-commutative Choquet boundary, which is minimal. But an example which I think might be more interesting to some of the people in the room is inspired from multivariate operator theory. So if you were to consider a regular unitarily invariant complete pick space on the unit ball, so you could think of particularly nice reproducing kernel Hilbert spaces like the Hardy space or Dury-Arvison space or Dirichlet space, then in fact these will all be satisfying this property. And the norm closure of the polynomial multipliers for this reproducing kernel Hilbert space does in fact have the Bishop property. So you can kind of view this as saying a kind of non-commutative function theoretic type of idea relating to the Choquet boundary and peaking phenomena. Okay, so in some sense you can relate the unique representing measures and the peak points in the non-commutative sense for these particular choice of algebras. And this builds up, this kind of is an application of some work of Hartz and Davidson. And I think it's a very nice kind of function theoretic fact. Okay, so in general, it seems like the ideas of peaking and peak projections and boundary representations, that you're able to establish a relationship between these properties, but in general, they're not always behaving too well, because you have these kinds of algebras that you can form from the extreme points that are not exposed and kind of build up kind of natural examples where you see possible failures arise. But in fact, there are also, on the flip side, some very nice examples which are completely natural and demonstrate a non-commutative function theoretic type of idea, which I think is fairly satisfying. Okay, so that's all I have to speak for today, but thank you for your time.